All right, so today we're going to talk about variability. So variability is an important part of our SOX. Basically, this is part of our S, or part of our spread. Okay, variability is this term that's used to describe how data values differ from each other and from the mean. So if the data values are similar to each other and they're similar to the mean, then they would have low variability. And if they are not very similar to each other and they're not very similar to the mean, they would have high variability or a large variability. Now, one way to talk about variability is range. So remember, range is the largest observation minus the smallest observation. And I have three data sets here. One ranges from 25 to 65. It has a range of 40. The second one ranges from 25 to 65. It has a range of 40. And the third one ranges from 25 to 65 with a range of 40. So here's the picture of what those three look like. So even though they have the exact same range, we don't have the same data set here. This is not doing a good enough job to describe this data. So we need another value for that. What I notice here is that these all have an average somewhere in this 45 range. And if you look, the green set down here, set C, this has the least variability of all of them. So even though they all have the same range, the values in this data set seem like on average to be closer to each other and also closer to the mean. The one at the top, these are on average more different from each other and more different from the mean itself. Okay, so variability is how much the data values differ from each other and also differ from that mean. All right, so low variability versus high variability. So we want to be able to quantify that. Now, sort of in general, more variability means you have a larger range, okay? But sometimes that's not a good enough measure for us to really get the full picture of what's going on here. I would like to be able to say, well, and here's what the data looks like in the center around the mean. So one way to think about this variability is that range happens to be sort of one of those non-resistant statistics. It's very far affected by those outside values. If we were to add another high value on this, the range would increase. If it would have a low value, the range would decrease. So we want to kind of center ourselves in the middle, which is why sometimes we would use interquartile range. That interquartile range does give us a measure of center that's around the median, though. So how do I talk about it in terms of the mean? All right, so one way we can talk about how things are different from the mean is to literally find the differences from the mean. Okay, so I have a sample of how far students live from school in miles, and just for an example here. So I've got 1, 2, 3, and 4. And those are my answers that I got to my survey. Here's a picture of what this would look like. I could find the mean. X bar is 10 divided by 4. That's 2.5. So on average, these students live 2.5 miles from school on average. Okay, and if I was to actually take each of these numbers, 1, 2, 3, 4, and subtract 2.5, we're off by 1.5 in this direction, 0.5, 0.5, and 1.5. So these are the actual differences from the mean. I could do the same thing. I have a little second example down here. And let me zoom out just a little bit. Okay, so with my second example here, I have 1, 1, 1, and 5. Now, if you're just looking at the data, that 1, 1, 1, and 5 seems like those values are closer to each other and closer to the mean on average. Okay, but if we were actually look at this data over here, here's my mean at 1 plus 1 plus 1 plus 5 divided by 4. This has a mean of 2, and you can see that these are really close to that, but you have this one that's really far away. So which one has more variability? So you might say, well, we just find all the differences and we add them together. So if I take x minus 2.5 and x minus 2, we end up with both of these having a sum of 0. So that doesn't really work. Okay, so if I want to find how different something from the mean, I have this problem that if I literally subtract and find the differences, I do have these differences, but they add up to 0. Both of them do. And in fact, this happens every single time. So one of the things that happens is that the sum of the deviations from the mean is always 0. Okay, so the way this works, if you were to take the difference of x minus x bar, or the difference between a data value minus the average data value, those always add up to 0, always. So even though that does give us the individual differences between the values, the sum is not a meaningful value for us to compare. So how do we try to get this done? So this is called standard deviation. And here's where the idea comes from. So we're going to talk about how this idea was developed or where this is coming from. We want to know, on average, how close a value is to the mean in our data set. So the first problem that we encounter when we're doing this is that the sum of the actual differences from the mean always add up to 0 every single time. Always. So just finding the differences and adding them together, because if I wanted to find an average, I'd add them up and divide by how many there are. But if I add all these differences up and divide by how many there are, I get 0 every single time. I would get 0 for both of these. On average, 0. On average, 0. 0 divided by 4, 0 divided by 4. That doesn't give me any difference in these two values. So there are a couple of ways to turn negative numbers positive, and the way that was used in the standard deviation calculation is by squaring it. So our first solution to the problem is by squaring those deviations from the mean. So instead of doing x minus x bar, we do x minus x bar squared. Now the benefit of this is all those negatives turns into positives, and we end up with a positive value. And this would be different for each data set. So if I scan back to that first page again, you know, up here, 1.5 squared, 0.5 squared, 0.5 squared, 1.5 squared, those give us 5. Down here, I would end up with 1 plus 1 plus 1 plus 9. Okay, so that actually ends up giving me, 12 there. So I do get differences. They don't add up to 0 anymore. So that solves the problem of making every data set the same. Unfortunately, we have two issues that arise from this problem solved. So we solve the problem and it creates a couple of more. Okay, so the first problem is that this is in squared units, because if you square miles, you end up with square miles. Okay, and the other is that we're trying to find a distance on average. On average, how far away are we from these values? And 5 doesn't seem like a very good representation. 1 plus 2 plus 3 plus 4, you know, we've got those values there. That doesn't seem to work. So this x minus x bar squared number, this 5, is a very large number, and it doesn't seem to represent a very typical kind of spread. It's too big. It's squared. So we want to find this average, and the number we have is just too big. So let's deal with the average part first. So to find an average, you would divide by the number of observations. Now, that's basically what this next step is, except for samples, instead of dividing by n, you divide by n minus 1. And I'm going to come back to that in a minute, so just put a pin in that for a second. So I'm going to take this 5, and I'm going to divide by n minus 1 because this was a sample, and I end up with 1.67 square miles. Now that tends to represent a sort of, on average, the distance away from the average. On average, the distance away from the average. So on average, these are about 1.67 miles away from that value 2.5. That was our original average there, okay? All right, now, again, we've got square miles. So since we have the average spread of the squared deviations now, we have square units. So we're going to solve that by taking the square root of that number. So I'm going to take my 1.67. I'm going to take the square root of that. So I took all the differences, I added them up, I squared them. Okay, and then I divide by that number to get the average. Now I'm square rooting that. That gives me my standard deviation. So the number before you take the square is called the variance, and the number after you take the square root is called the standard deviation. Now, standard deviation is also a non-resistant statistic. If you throw outliers in there, it's going to cause your value to change dramatically in one direction or the other. Okay. Also, I don't expect you to be able to derive this from scratch, but you do need to understand how this formula works and how to interpret standard deviation. So standard deviation is the average deviation from the mean. It's like saying this quantity, this standard 1.29 miles, is a typical deviation, is a typical difference between the values we saw and the mean number of miles. So this would be, if I was going to interpret this 1.29 miles, I would say 1.29 miles is a typical deviation between an observed distance from school and the mean 2.5 miles. Okay, so on average, we're about 1.29 miles away from the average. Okay, so the larger the standard deviation is, the more variability our data set has. It's a way for us to describe those numbers in the middle. If I was to go back to that very first picture in class, okay, even though the ranges are the same in this picture, I would expect the one that's part C here in green to have the smallest standard deviation, because the differences between the observed values and the mean are on average smaller than they are in A or B. Okay, so standard deviation helps us talk about, on average, how do these values differ. Now, when you are dealing with standard deviation, just like with our other things, mean, we've got X bar and we've got mu. For proportions, we've got P hat and we've got P. We've got this idea of a population number and a sample number. So with population and sample, we use sigma, which is this little O with a nose. That's that Greek letter lowercase sigma to represent the standard deviation of a population. And we use the English letter S to represent the sample standard deviation. So that means if you go to run this in your calculator, remember your calculator is going to give you both values back. It's going to give you the S standard deviation and the sigma standard deviation. And the reason why those are a little bit different from each other is because population standard deviation, the average is conducted using that capital N, that total sample size, or sorry, total population size, total number of observations, whereas sample standard deviation is N-1. So because the divisor is a little bit smaller, it makes that standard deviation calculation a little bit bigger. All right, so what do you have to know how to do? Again, you need to identify, yes, this is my formula for standard deviation. This is my formula for standard deviation. Both of these are going to be on your AP Statistics formula sheet. You need to be able to compute this in your TI-Nspire and get the number out of here, but you're probably not going to have to calculate standard deviation by hand too often. Okay, most of the time if I'm asked for standard deviation, I've got my TI-Nspire, I'm going to plug through those one variable statistics, I'm going to get those numbers out of there. But you have to know which one is which. So I know that if I entered sample data, I'm going to use this first number and I'm going to ignore the second one. Or if I know I entered population data, I'm going to use the second number as my standard deviation and I'm going to ignore the first number. Okay, so here's the sort of theory behind this that you do need to understand. So why do we square the standard? Like here's my standard deviation formula up here. Why is that numerator squared and then square rooted? Like what's the whole point of squaring the differences and then square rooting those? So it's because that in your differences between every data value and the mean always add up to 0 every single time. So if every data set has the same sum of 0, this is not a good way of distinguishing them between them. It doesn't give us a meaningful difference or a meaningful average distance or whatever. So when you square those values, the negatives turn positive and you yield a much more meaningful sum. You're really dealing more with difference as a distance now instead of difference as a raw value, which is always going to be 0. Okay, why do we use the N-1 instead of the N for sample variance? Or in other words, why are we dividing by N-1 to find an average? Because average, you add them up, divide by how many there are. That's how it always works. So that's how it works for an average. Why is that not how we're dealing with the standard deviation? Why are we not dividing by N instead of in minus? Why, right? Why do we find the average that way? So I'm going to go back to a picture we had in chapter 1. So we had a population here, and then the question was, how do these samples that were drawn from this population look like this value? And one of the things I want you to remember is that the range, when we looked at the samples, every single sample had a smaller range than the population did. That's because none of the samples included this value 11 in any of them. That value never got selected. Okay, so the idea is when we're talking about spread values, we're talking about range, we're talking about standard deviation, any of these spread values. When you take a sample from the population, you almost never get the extreme max and min in your sample. It's just statistically that doesn't happen every single time. It's just doesn't happen. Could happen, absolutely, but doesn't happen. So if you're not getting the extreme values in every sample, that means that your range number is always a little too small. Or if you're not getting that maximum and minimum value, your standard deviation calculation is always going to be a little too small. It's not going to include those biggest differences that exist there. Now, you don't have that problem with means. Sometimes the mean is a little bigger and sometimes the mean is a little smaller. And they sort of average out to the right number. But with, spread, they're always a little too small. So if your whole purpose in statistics is to try to compare a population or try to inference back to a population and you're dealing with your sample, then if you know your number is definitely going to be too small, you can kind of adjust for that. And that's what this does. So we're anticipating that standard deviation, that's a measure of spread, almost always is going to underestimate population spread. Okay, the sample spread values almost always underestimate that. So we're trying to predict what population is, and we know that when we take samples, those spread numbers are probably going to be too small. So instead of dividing by n, we're going to divide by n minus 1, with the idea that if you divide by a number that's a little smaller, your overall result is going to be a little bigger. What this does is this inflates our sample standard deviation a little bit and makes it more likely to be a better estimation of sigma. Okay, so just again, when you read in your calculator, okay, this is not saying that both of these numbers are correct, but one of them is n and one of them is n minus 1. So this number has been inflated because it knows that if this data was drawn for a sample, then the real standard deviation is probably not 1.29. Okay, it's probably a little bigger, so it naturally inflates it, gives you that n minus 1, and gives you that 1.32, and that makes it a better estimate for what the true value is. Okay, the other question is why the square root instead of the square? Like, why are we square rooting this? Why is standard deviation a square? And it's because, for one, because this is a smaller value as an estimate, it also makes it in the same units as our means. So we had square units, now we have, so we did have units that were squared, now we have units that match our mean. That should be in regular units. So when you square all those values to get rid of the negatives, you end up, and then you divide to find the average, you get the average squared distance. It's much easier to compare miles to miles than it is square miles to miles. So that just matches, it sort of undoes that, that distance formula that we've been doing. Okay, and then finally, when is it appropriate to choose mean and standard deviation for your center and spread instead of our mean, median, and interquartile range? So why would you want to use for your SOCs, okay, when would you want to use the mean as the center and the standard deviation as your spread as opposed to median and interquartile range? Okay, so if your distribution is skewed, okay, or has extreme values, most of the time we want to use median because remember, median is a resistant statistic to those. That's a better representation of a typical value and a typical difference. And so if you're going to use median, that pairs up with interquartile range. If your distribution is roughly symmetric or it doesn't have extreme outliers, you want to use mean and standard deviation. Okay, so other things. What happens to the mean and what happens to the standard deviation if you get rid of a large outlier? All right, so if I'm talking about my mean, if I had a really high outlier that didn't seem to fit, okay, and I remove it. So let's say that you had a bunch of tests and you have a whole bunch of like 70s and you have a 105 you got on a test, and I say, I'm dropping that score. That wasn't reasonable. What happens to your average? You drop that high number, your mean is going to drop as well. Okay. Now, as far as standard deviation, that high number had a big residual value, had a big difference between the mean and the value itself. So if I get rid of that big difference in my average distance calculation, that means that standard deviation is going to go down as well. It's going to kind of decrease that spread, and when you decrease the spread, you're going to decrease that standard deviation. If I introduce a really low outlier, so let's say that you've taken a test, you've gotten like 75s on all your tests, and then suddenly you come in and you get a 2. Eek. That's going to decrease your mean. Your mean is going to go down. That average going to drop. What about standard deviation? So I have my data set here, and then all of a sudden I introduce a really low value over here. That's going to increase that spread, okay? And that's going to increase the average distance from the mean. That's going to cause our standard deviation to go up. Okay, so introducing a low outlier, even though it's a low value, the difference is what matters. The distance away from the average is what makes a difference there. If you increase your sample size, all right, so if I increase my sample size, my mean is probably going to just become more accurate. Okay, so it's probably not going to change too much. It could go up, it could go down, but if your sample is larger, your mean is probably a more accurate value, okay, of your sample to your population. The standard deviation, though, if you think about this formula, so again, it's the sum of every number minus the mean squared to make it positive, on average, divided by n minus 1, and I take that standard deviation. If I get a bigger sample, it's going to increase that sample size in my denominator, which is probably, if I'm increasing the denominator, I'm probably going to be decreasing the overall standard deviation. Everything else remaining the same, a larger sample is going to do that. Okay? All right, so if you were asked to find the indicated statistics for each data set, I've got my TI-Nspire here. I'm just going to run those one variable statistics. So if it says, hey, find the mean, find the standard deviation, find the median, find the interquartile, there's no reason why that you need to do these by hand. I mean, you could. It's totally fine to do this, but you don't need to do the standard deviation calculation by hand as long as you have your calculator. So I have already into my calculator. My computer is happy to give me notifications here in the corner. I've already got these typed into my calculator. I have list A and I have list B. And I just want you to notice the only thing that's different in these two lists is that this one has a 160 and the other one has a 16. All right, so I've got them in here, and I'm going to go Menu, Statistics, Stat Calculations, and one variable statistics. And it says number of lists. I'm just going to go ahead and keep selecting one here. It says my X1 list. All right, so I'm going to click down here. I'm going to say A. Okay, and there's no frequency or categories here. Ooh, that makes me nervous. Let me see where I'm at. I'm going to go over here and do this instead. Menu, Statistics, Stat Calculations, one variable statistics, one list. That is list A. I'm going to click OK. And I'm going to get X bar. Okay, there's my mean. I know this was from a sample because the problem told me it was from a sample. So there's my standard deviation. Okay, I'm going to use the S one here. I'm going to need my median. That's 8. It asks for interquartile range. So Q3 is 12 and Q1 is 4. And I should be able to use that data. I'm going to go over here. I'm going to run the other set of data now. So Menu, Statistics, Stat Calculations. Oh, I hit linear regression again. Menu, Statistics, Stat Calculations, one variable statistics. Again, I'm going to say I've got one list. This time, I'm going to run set B. Click OK. Okay. I can see my median here is also 8. My Q3 and Q1 are still 8 and 4. That gives me a difference of 8. My standard deviation now is huge, 46 instead of 4.6. And my mean of this second set of data is 21.6. All right, so I'm going to come back over here and write these numbers down. This is 8.55. This is 4.66. This is 8. Q3 was 12. Q1 was 4. That gives me an interquartile range of 8. And it says, what do you think the shape is? So the mean is 8.55. The median is 8. That's really close. Okay, those are pretty close. So I'm going to say I think that this is approximately symmetric. Okay, and this is just a guess because I don't have this data. If it's not approximately symmetric, then I could say, well, the mean is slightly larger, which means that the mean could be on the right. It might be slightly skewed to the right. All right, my mean of the second set was 21.64. I had a standard deviation of 46.06. The median was still 8. The interquartile range was still 12 minus 4, or 8. And this shape, the mean is significantly larger than the median. That means if we were to put them on the number line, the mean would be to the right. The mean follows the skew, so I would expect this to be skewed to the right. Okay. Now, one of the things you're supposed to be able to do is make interpretations and code. This isn't exactly in your notes, but I want to include it in the video for the people that weren't here. So interpret the mean and the standard deviation in context for sample A. All right, so, and let's assume these represent the number of multiple choice practice questions answered last weekend by a sample of AP Statistics students. So for the mean, I would type in something like 8.55 questions is a typical number of questions answered by students in this sample of AP Stats students. All right, so 8.55 is a typical number of questions from this sample. Typical value of questions. Okay, I got my variable there. And then for my standard deviation was 4.66. So I'd say 4.66 questions is a typical deviation. Oh, I can't spell. It's a typical deviation between the number of questions answered or observed and the mean of 8.55 questions. So again, that idea is that the mean is a typical value of the variable in this sample. The standard deviation is a typical difference, typical deviation between any given observed value, okay, an average difference in the differences, okay, and our mean. So you want to have included in those values there. Okay, one last thing very quickly here. One thing that you need to be able to do is read something called Minitab Output or read computer output. We have several chapters where we're going to have to deal with this, but here's a little example of if you had a computer program that spit out this information, you might get something that looks like what's on the screen here. And so this has variable acrylamide, we've got n equals 7, and just be able to pick out these values here. So you notice there's a mean and a median. There's this thing called trimean. We're going to ignore that for right now. Standard deviation, okay, SASE mean, we're going to ignore that for right now. So we've got my standard deviation, my mean, and my median. You see the minimum and maximum, Q1, Q3. I, from that, could give my interquartile range by subtracting. You can get the range by doing the maximum minus the minimum. You could test for outliers using that 1.5 interquartile rule against those maximum and minimums. And you could make a guess about what the shape here. Here, since the mean is greater than the median on a number line, that put the mean to the right, and the mean follows the skew. All right. So, standard deviation. Can you get it from your calculator? Can you interpret it in context? Do you have a basic idea of how standard deviation changes when you add or subtract extreme values? Those are your most important things there. Other things that are important are, do you understand why standard deviation formula works like it is? We're trying to find this average distance. Since those distance differences always add up to 0, we square them. We're looking for an average distance, so we divide by the number of values. We're dividing by n minus 1 for samples because samples tend to underestimate spread values. So a smaller number inflates it just a little bit, makes it a better approximation for what's true. Okay. We square root it to make the units match again. That gives us that distance.